only thing surprising is the temperature gradient. At face value, you'd expect that the higher up you get, the colder it would get, as simple as that. But as we saw on Mage, that's not the case. We started off about 12 degrees centigrade, and as we went up through the troposphere, the temperature dropped fairly steadily to about minus 35 degrees. This would be roughly the point where we move from the troposphere to the stratosphere. Now, the reason the troposphere is warmer at the bottom is, of course, it's heated by the Earth, which is heat reflected from the sun. As you go higher and get further away, there's less heat, which actually does leave you with an interesting problem. You've got the cooler, heavier air above the warmer air, and of course, cool air wants to sink and warm air rise, so you get a lot of mixing. That's why all our weather occurs in the troposphere. After a point, through the stratosphere, of course, of cold air, that's more stable, so that doesn't tend to mix. As a check, I found a diagram on the internet, and you can see that as you rise with height, the temperature drops until you reach the top of the troposphere. Then after a while, the temperature starts rising again as you pass through the stratosphere. Of course, we only made it about 3/4 of the way up. So little Mage, as far up as she went, validated known science. I think we'll chalk that up as win one for Mage. Now, the next thing to look at is atmospheric pressure. Now, as we know, the atmospheric pressure is...
Thanks to old Mage, she validated flat Earth. Earth is supposed to be flying through infinite outer space, chasing the sun at 500,000 miles per hour. But this balloon is taking great video shots of Earth. It don't look like it's flying. Earth don't look like it's flying either.
Nothing more than the weight of the atmosphere above pressing down. So it makes sense that at the bottom you've got the entire atmosphere above you pressing down. As you go further and further up, there is less and less of that. So you should end up with a nice, gentle curve. And that's exactly what we found with Mage. Now, the atmosphere is held down by gravity, and at any point along that curve, the pressure just above and just below is virtually identical to that at that point. So this is why there's no reason for the atmosphere suddenly to rush in one direction or another to try and equalise, because at any point, the atmosphere surrounding it is basically at exactly the same pressure. This is a very, very smooth and fine gradient. What we don't have is a pressure of, say, 100,000 pascals next to a pressure of 50,000 pascals. Because yes, under those circumstances, it would equalise very, very quickly. So once more, Mage has taken measurements that agree with known science. Chalk up number 2 to Mage. But rather than just readings, I think that Mage can do a little better than that. I think it's time we had a close look at the balloon camera. Now, at launch, it's actually really hard to make out the balloon because of the clouds above. So what we'll do is we'll jump forward till we've just come out the top of the clouds. Great stuff. So let's grab that balloon cam and freeze frame it at 1,400 meters. We'll do screen grabs at a couple more heights and then just before burst point. Grab the balloon cam and freeze frame just under 20 kilometers. We do the same again, just approaching 30 kilometers. Grab the camera and then take a freeze frame. And we grab the balloon camera for one last time and freeze it just before it's about to burst. The amount of hydrogen in the weather balloon is constant throughout the flight. However, the atmospheric pressure is reducing. As that pressure reduces, there is less resistance to the pressure of the hydrogen on the inside of the balloon, which therefore expands. It keeps expanding until the balloon can no longer take it, and it bursts. So Mage has demonstrated the temperature gradient the pressure gradient, and now visually it has shown us the massive effect that the reducing atmospheric pressure can have as you rise in height. There's only one thing left: Earth curve. So let's start off by looking through Mage's camera. Now this image has not been taken at any great height, but even when we're at the peak of Mage's journey, we're not going to easily see the curve. It's only very slight. So these reference lines serve two purposes. Firstly, there's something to compare any curve against, and secondly, they're to demonstrate that the image itself has not been manipulated. There's a simple technique to accentuate any curves to enable them to be seen more easily. That's to compress the image from left to right in its width. Now the interesting thing is only curves get accentuated. If we add a number of random straight lines on this image and then compress it, those straight lines remain straight. The angle of them changes, but they remain straight. Curves are accentuated. This technique is so effective, it actually shows us a slight problem. That bottom Mage string is straight. The issue is the tiny amount of barrel lens distortion in a non-distorting camera. It still gives us a slight curve. But as we can see from the diagram on barrel distortion, lines below the centre line are concave. The Earth shape that we're looking for is convex. So if anything, this distortion works against Mage. It will make a curve look flatter. If the Earth is flat, it will make it look convex, not concave. Let's have a look at the images. This first Mage image is at 33,456 metres. Absolutely gorgeous. Now the horizon line is just into the top third of the image. This means that the barrel distortion will actually make the Earth look more curved than it really is. So it's not a fair test for flat against curved, but it's interesting to look at it. So let's compress the image and now add a horizontal, perfectly straight line so we've got something to compare against. I think that's quite obvious that there is curvature. Let's zoom in a bit. So yes, curvature can be seen, but this is in the upper third of the Mage camera, where some barrel distortion will make curves look more pronounced. So we won't regard that one as a test. However, I would like to point out that the Mage reference line still looks straight. Let's have a look at something across the middle of the camera. Now this drop-dead gorgeous image is at 35,160 odd metres. It is stunning. There is no doubt that there is curve there. That horizon line is across the middle of the field of view. So barrel distortion up or down is not going to be taking effect. That is a smoking gun. But let's have a look at it compressed. And I'll add a horizontal yellow line again for completeness. Oh look, we done got curve. I'd say it's game over for flat Earth. But I think Mage can do just that little bit better. We've seen the image of the horizon line just into the top third of the screen, where barrel distortion would help. We've now seen a horizon across the centre of the field of view, where barrel distortion should neither help nor hinder. How about the bottom third? So any distortion is working directly against seeing a curved horizon. Let's go for it. 37,705 metres in the bottom third of the screen with barrel distortion working against it, we can see curve. Let's compress it. There is definite curve there, and you can see it's curving the opposite way to the reference string, which is only curved because of barrel distortion. Let's add that yellow line just for completeness. And there we go. Globe Earth. Suck it up, princess. I think there's one last thing to do. Let's go back to that gorgeous image. If you recall, at the beginning of the video, I showed you that graphic that Andre Puelma had produced that shows the calculated curve that we should see at the height of 39 kilometres. In this image, we're just at 35, but let's see how it does if we overlay it. Not bad. Not bad at all. Well, surprising is the